Good morning, class, and welcome to this lesson on Momentum 1, momentum and impulse, okay? Today we will be able to define momentum and impulse and describe how they relate to each other qualitatively and quantitatively. So we're going to look at some situations and kind of be able to describe what's going on and also look at some numbers as well. So here we go. So what is momentum? Momentum is defined Momentum is defined as the product of objects and objects' mass and objects' mass and its velocity. Momentum is a common word we might use in everyday language. If something is very heavy and it is moving, we go, oh, that has a lot of momentum. For example, if a car was rolling down the parking lot, like in our North student lot, you wouldn't get in the way. And if someone said, how come you didn't stop it? A very common phrase would be, well, because it has a lot of momentum. So a momentum is something we kind of understand, and we tend to equate it with heavier objects. But the reality is it could be any object that has mass and it's moving. Okay? It's also kind of known as inertia. Inertia in motion. So remember that we talked about inertia. Inertia is really related. Inertia is very related to mass. Okay? A big boulder would like to stay at rest more than a very small pebble, right? Inertia is mass, and so inertia in motion is mass and velocity. So the symbol for momentum is P. I don't know why it's P. It just is. Better than M, honestly, because if it was M, we'd have another M we have to throw in there, and we have enough M's already with meters and mass. So the symbol for momentum is P, and so P equals M times V, an object's momentum. Okay? So, and like I said before, it's for any object. It's for any object. Okay, not just heavy ones. And so, for example, these numbers could be off slightly, but the concept is still there. Let's take a bullet. A bullet, we'll say, weighs 0.01 kilograms, and it's traveling 500 meters per second. Well, our momentum of this would equal 5 kilograms times meters per second. By the way, kilograms, meters per second is the unit for momentum. Okay, it doesn't have a fancy name like Newton or Joule or Watt. It's just kilograms meters per second. This is going to be our unit. Okay. So a bullet has a momentum, and let's say we have a bowling ball, and its momentum is 5 kilograms, and it's traveling 1 meter a second. Okay, so its momentum is going to be 5 kilograms meters per second. Notice the bullet and the bowling ball have the exact same momentum, despite one being very, very small, although it's going very, very fast. Okay, very, very small, but very, very fast. A bowling ball is much, much larger, but it's moving much slower. These two have the same momentum, okay? It would take the same amount of force to stop both of these, okay? We'll get to that in a second, okay? Like I said, I'm not sure if these numbers are realistic. I know this one is slightly realistic. I haven't looked up the mass of a bullet in a while, or how fast they travel, but just go with that for right now. The concept is these have the same momentum despite being very, very different objects. They have mass, they're moving, they have a momentum. So let's go to the next page now. Let's talk about impulse. Impulse. Impulse is defined as a force applied over a period of time to change an object's momentum. this is where things start to get interesting. The reality is here, momentum, this is just a quantity. It is just a straight quantity. Oh, and by the way, this is a vector quantity because velocity is a vector. Velocity is a vector, momentum is a vector. Okay, so direction matters. Okay, but momentum by itself is really, what does it matter? Okay, it has momentum. It's moving, it has mass. What's the big deal? In science, really the fundamental thing with science is we like to see we like to change things and see what happens. We want to do something to an object and make it change and see how that works and see why it worked that way. So impulse, when we apply a force over a period of time, we change an object's momentum. So now we're actually getting into somewhere. If I want to change an object from moving to not moving, what force do I have to apply and how long do I have to apply it? That's a serious question, and that can apply to a lot of different things. So impulse is known as J. Why J? Once again, don't know. And as force, I'm going to put average force times delta T. It is a force applied over a period of time to produce an impulse. Okay? J is impulse. Now, notice, force applied over a period of time change an object's momentum. Well, we have now what I'm about to introduce you, what's called the impulse. This is called the impulse momentum theorem. Impulse momentum theorem. Okay? So the impulse momentum theorem is this. F delta T equals the change in momentum. And most of the time, it's going to be equals m delta v. Most times, every problem we do in this class is going to be because of change in velocity. The mass could change too. We could have a change in mass and a constant velocity. For example, in the example of a rocket ship going into space, as it flies up, it is losing mass because the fuel is being ejected out the back. So, but we're not going to deal with that. Okay, that's not going to be the focus for this class. We're going to focus mostly on this. So this is going to be our equation. A force, an average force applied over a period of time equals a mass times the change in velocity. This is the impulse momentum theorem. So if I want to get an object to from 20 meters a second to 0, okay, change in velocity, or from 0, final minus initial, so from 0 to 20, what force do I have to apply and how long do I have to apply it in order to get it to do that? Okay, so once again, what force do I have to apply and how long do I have to apply it to make this mass change its speed? Okay, so let's look at an example, a very common example. Let's look at, and this is going to be conceptual, okay? Oh, excuse me. I'm going to go back a second right now. Okay, notice this is a graph. This is a graph of the force and time, F delta T, of a bat hitting a ball. Now, this ball is going to be in contact with this bat. You know, the bat is here, contact with the ball, and it's going to be in contact with that ball all the way out here, okay? So this ball is going to travel along this bat, and it's only for like a millisecond or a few milliseconds there. It's going to be in contact with that as it travels from here to here. So it's going to be in contact with the bat for a certain period of time, and there's going to be a force applied. Notice this force is variable. This is a variable force. It is not constant, okay? This is a variable force, but this is the average force. And this average force, if we took this graph right here, the area under this graph, if we moved it down here, would be equal, the area of this one would be equal to the area of that one, okay? So the average force multiplied by time gives us our impulse, okay? So, sorry, I had to go back for a second on that one. Let's look at an example of someone hitting a tennis ball. This is just like the bat. Okay, this is just like the bat. Notice this person changed clothes in the process of hitting the ball. It's very, very crazy. So notice when this person hits a tennis ball, the ball comes in contact with the racket here. So therefore a force is applied. The force is applied for a certain period of time. It is applied from this point to this point, delta t. Okay? That means this mass, this tennis ball, is going to change its velocity. Let's say it was going 30 meters a second that way, and now it's going, make it easy, change it, 40 meters a second that way. M delta v. So, remember, velocity is a vector. We'll call to the right positive. Okay, we'll call to the right positive. And so that means positive 40 final, so positive 40 meters a second, this is final momentum, minus a negative 30 meters a second equals what? So if we apply a force over this period of time, we will get m times 70 meters per second. This is the change in velocity. So if I want to change a tennis ball's velocity by 70 meters a second, I have to apply a certain force over a certain period of time. Okay? Force multiplied by time gives us momentum. Now, this is where this gets very interesting. Okay? Here are two examples of a car, same car, same momentum, crashing into a haystack, crashing into a wall. Okay? Crashing into a haystack, crashing into a wall. Now, let's say this car is going from, 50 meters a second to 50 meters a second, excuse me. 0, oh my gosh. 0 is the final speed, and 50 is the initial speed. Yeah, so this is our delta V. Here's m. Okay? Both cars are going from 50 to 0. They're both going 50. They're both going 50, and both end up at 0. Okay, both end up at 0. Okay? They are traveling at a certain speed. Both are traveling, both stop. In this case, when we hit this haystack, the car slows down slowly. This car slows down slowly. So if we look at this equation over here, in this situation up top, we have a very, very large amount of time that this car slows down, so that means the force can be smaller. That means the force can be smaller because this number over here is constant. Let's say the car is, 500 kilograms, okay? 500 kilograms, and so we end up getting 500 times 50. So the change in momentum here is 25,000 kilograms meters per second. I'm sorry this is a little messy. It's not very organized. Please do your best, okay? This car is going from a very high, the change in momentum is this. It is the same for both situations, okay? 50 to 0, the same momentum. But this one, because it's going to stop slowly, it's going to stop for a long period of time. The force on the car is going to be smaller, therefore no damage. Small force, no damage. This one's going to crash into a wall and stop very, very quickly. It's going to stop extremely quickly. And so it's going to have a very, very large force over a very small period of time. Notice, the change in momentum is the same for both. One used a very, very small force over a longer period of time. One used a very, very big force over a shorter period of time to stop it, but the result is the same. It goes from 50 to 0. But this is a big difference for your car. When you apply a larger force, you get more damage. When you apply a smaller force, you get no damage. Okay? So this is really how it comes in. When we design things, anything that moves, cars, planes, anything, or just any objects, what's it going to take to redirect that object? And what force do we have to apply, and how much time do we have to apply it? Okay? And all based on the situation is going to depend on what we need to do. Okay? So that is the impulse momentum theorem. This is the same thing with the bat. We have a velocity going in, we have a force, we have a velocity going out. This is in the book, don't worry about that. So impulse momentum theorem, force times time equals m delta v. The change in momentum is the same for both. But what force do we apply and how long do we apply it to make a change?